Hello, my name is Bernardo Martinez. I'm a PhD student at West Virginia University. I'm working under Dr. Guilherme Pereira at the Field and Area Robotics Laboratory, and I'm here to talk a little bit about my work. It's called Fast Path Computation using lattices in sensor space for forest navigation. The motivation for our work is developing robotic systems that are able to autonomously operate, to navigate, and to complete tasks in unstructured, densely populated, and dynamic environments without prior knowledge of where the obstacles are located. As mobile robots are becoming increasingly accessible, we want traditional industries to take advantage of them. For example, we have identified that aerial robots can help fighting wildfires, can help maintaining forest inventories, and they can help with pest control by identifying bugs or pests. However, we know that drones, for example, have very low autonomy and they need to be fast to complete the proposed task before running out of battery. While there are many limiting factors for the speed of these kind of robots, some of them are just part of the specifications of the problem. But motion planning, however, is certainly one of the factors that we can improve. So that if we can plan fast, we can move fast as well. In our work, we developed a motion planner which uses a lattice in sensor space, as you can see in this picture here, which computes paths as fast as a sensor, in this case is a LiDAR, can generate new data. This planner sets a search tree that contains all possible paths that a robot can take locally. It stores mappings between laser beams and graph edges, and it also has a vector field that encodes a global task we want to accomplish. And the basic idea is that in real time, we just prune the edges that would lead to collision, as the ones in red in this figure. And then we assign costs to, according to the vector field to the remaining ones, and then we select the path that minimizes the cost. So the first step is to actually generate the lattice. In our work, we made it highly parametric in a manner that we can define how many layers, how many trunks, which are the edges leaving the root node, and how many branches the lattice would have. The graph itself we organize as a tree so that the search is trivial and very efficient. And once a node is selected, there is a single path between it and the root node. And then another cool thing is that we selected a spatial representation that allows triangulation. Therefore, the space around the sensor is fully covered, and that makes collision checking easier. In order to quickly prune the edges that would lead to collision, we compute two mappings. The first one associates two neighbor triangles of each of the edges, as the one represented here in blue. And the second one associates all the triangles that are intersected by a laser beam, as in the lower figure. And then for actually checking for collision, we do these three steps. First, when a range measurement comes, we filter it to check if the measurement is inside of the lattice radius. If it is, we grow the measurement by a radius representing the size of the robot. And then for the circle, we check if there's any overlap with any of the triangles. And if there is, we mark this triangle as in collision. And then using the relationships that we developed before, we can check which are the edges that need to be pruned. Another cool thing about our method is that collision checking can be easily parallelized, since there is no overlap of triangles, and the range measurements can be tested with each of the triangles separately. In our most version of our code, we parallelized our motion planning by simply assigning triangles to the blocks of a CUDA-enabled GPU, and we assigned laser measurements to each of the threads in these blocks. Then all the collision checks can be performed simultaneously. This is very important because, of course, collision detection and collision checking represents the most expensive component of our planner. So now that we know how to prune the lattice and we know how to make this very fast, we still need to select from the remaining paths which is the best. So in our work, we encode global task as a vector field that leads to a desired behavior for the mobile robot without considering explicitly the obstacles. This vector field can be defined in any way, but in here we're taking advantage of an idea of a previous research in our group, in which we select a curve in space that we want the robot to navigate in. Then for each point in space, we combine a normal vector that attracts to this curve and a tangential vector that makes it drive along this curve. So, for example, if we place the robot outside of the desired curve, represented by the dashed line, just by following the vector field, we guarantee that the robot will eventually converge to the curve. After pruning, we use a simple BFS algorithm to assign costs to each of the vertices of the tree. These costs are obtained by using a function that measures how aligned a given edge is with respect to the vector field. So if a robot is going from vertex I to vertex J, for example, and it's perfectly aligned with the field, the cost of traversing it is 0. If not, the cost is increased up to a maximum where the vector field is pointing in the opposite direction. The outer layer is then sorted by the costs, and we select the node with minimum cost. As our graph is represented by a tree, we follow the pointers to the parent vertices until the root, and then this, of course, will define the optimal path. The search operation has a very low computational cost just because we are using a tree. To show what happens in real time, we simulated it with using some of the tools in the navigation toolbox in MATLAB. In here, we are representing the robot as a punctual holonomic robot, and we gave it range measurements. We're considering a single integrator model for the dynamics, and we placed the robot in a Poisson forest. As you can see, as the robot moves, the obstacles are sensed by the LiDAR, and triangles are marked in red. And then the optimal path is shown in green. In this simulator, we tried a couple of different obstacle densities just to check the performance of the planner. As we were expecting, without having prior knowledge of the obstacles, as we increase the density of obstacles in the map, even though we are selecting optimal paths locally, we obtain a lower quality for the paths in the long run whenever we have this higher density. Another thing that we noticed is that, as expected, the maximum computing time of each iteration is dependent only on the parameters of the lattice. And that's just because in the worst case scenario, we will just need to check, make a number of calculations proportional to the number of laser beams times the number of edges in the graph. In here, you can see a sample of the experiments we conducted in our lab. In here, we had create two robot with 360 degrees LiDAR on top of it, and we were using G mapping for our localization. And once the robot is turned on, it wants to follow a straight path in the direction it's started. But of course, it has no knowledge of the obstacles, which in here are represented by these cylinders as trees in a forest. And then just by acquiring that data from the LiDAR, it's able to produce paths that guarantee collision avoidance. And we also have conducted some experiments to compare our method with standard implementation of RRT star that we got from OMPL library. And we noticed that if we give our RRT star sufficient time and information about the obstacles, it will generate an optimal path that follows the vector field even better than our code. But if we give RRT star the same time that our planner has to generate its paths, RRT star will actually generate very different paths with a high dispersion. So we believe that our method is able to generate these paths in a more robust way. Here I show you some results for collision checking after we parallelize our code. And as you can see, the collision check time, which is actually the biggest chunk of the total planning time, became basically invariant to the number of obstacles that is seen in the sensor space, and also to the discretization of the sensor space, which in here is represented by the number of triangles in the lattice, but it can also be represented by the number of edges. And then in the end, we were able to get a speed up of at least 1 order of magnitude, just by making it parallel. To summarize, I introduced you to this new motion planner that we created, which tracks a vector field, and it's able to handle obstacles in its local field of view for the sensor. I showed a way to generate this lattice using some parameters, and I showed a strategy to prune the graph using some pre-computed mappings. I also showed a little bit about how this this motion planner can be made parallel, and just by making our code parallel, we were able to generate paths in less than 10 milliseconds, which is half of the time that the sensor needs generates its data. And with that, I conclude my presentation, and thank you for your time. And if you have any questions, I'm glad to take them. This is our website, and this is the handle of our Twitter. Thank you again.